How machine learning actually works. Hook, 20 seconds. Every time you unlock your phone with Face ID, Netflix recommends a show, or your email blocks spam, you're witnessing something that would have been considered pure magic just decades ago. A computer is making intelligent decisions without being explicitly programmed for every possible scenario. Context, 40 seconds. Welcome back to AI Fundamentals Explained. In our previous episode, we explored what artificial intelligence really is and discovered that most AI today isn't the sci-fi superintelligence we imagine, but rather specialized systems solving specific problems. Today, we're diving deeper into the engine that powers most modern AI, machine learning. By the end of this episode, you'll understand exactly how computers learn to recognize patterns, make predictions, and get smarter over time, without being programmed for every single task. Section 1. The Fundamental Breakthrough, 90 seconds. Here's the revolutionary idea behind machine learning. Instead of writing specific instructions for every possible situation, we show computers thousands of examples and let them figure out the patterns themselves. Think of it like teaching a child to recognize dogs. You don't give them a precise technical specification: forelegs, fur, wet nose, tail. Instead, you show them hundreds of different dogs and say, that's a dog, that's not a dog. Eventually, they learn to identify dogs they've never seen before. Machine learning works the same way. We feed algorithms massive amounts of data, images, text, numbers, sounds, along with the correct answers. The algorithm analyzes this training data, identifies patterns, and builds a mathematical model that can make predictions about new, unseen data. But here's what nobody talks about. The quality of your training data determines everything. Feed an algorithm biased or incomplete examples, and it will make biased or incomplete predictions. This is why companies like Google and Facebook spend billions collecting and cleaning data. Section 2. The 3 types of learning, 120 seconds. Machine learning comes in 3 flavors, and understanding the difference is crucial. First, supervised learning, the most common type. Here, we provide both input data and the correct answers. It's like studying for a test with an answer key. Show an algorithm 10,000 photos labeled cat or dog, and it learns to classify new photos correctly. Unsupervised learning is trickier. We give the algorithm data, but no answers. It has to find hidden patterns on its own. Imagine dumping 50,000 customer records on your desk and asking, "What groups do you see?" The algorithm might discover that customers naturally cluster into segments based on buying behavior you never noticed. Then there's reinforcement learning, the game changer. Here, the algorithm learns through trial and error, receiving rewards for good decisions and penalties for bad ones. This is how DeepMind's AlphaGo became the world's greatest Go player and how ChatGPT learned to have helpful conversations. The fascinating part? Reinforcement learning is closer to how humans actually learn. We don't memorize every possible conversation before talking to people. We learn what works through experience and feedback. Section 3. How algorithms actually learn, 140 seconds. Now let's get into the mechanics. When we say an algorithm learns, what's actually happening under the hood? At its core, machine learning is sophisticated pattern matching through statistics and mathematics. The algorithm starts with random guesses. Imagine trying to draw a line through scattered data points while blindfolded. With each example, the algorithm measures how wrong it was and adjusts its internal parameters slightly. It's like adjusting the angle and position of that line to better fit the data points. After seeing thousands or millions of examples, these tiny adjustments add up to accurate predictions. The mathematical magic happens through something called gradient descent. Think of it as rolling a ball down a hill to find the lowest point, except the hill represents the algorithm's errors, and the lowest point represents the best possible accuracy. But here's where it gets really interesting. Modern algorithms don't just draw simple lines. They create incredibly complex mathematical functions with millions or billions of parameters. A single image recognition model might have 175 billion parameters, more than there are stars in our galaxy. The result? These algorithms can capture subtle patterns that humans would never notice. They might discover that certain combinations of pixels predict skin cancer better than dermatologists, or that specific word patterns indicate depression in social media posts. Section 4. The data problem. 100 seconds. Here's the dirty secret of machine learning. It's actually more about data engineering than algorithms. The fanciest algorithm in the world is useless without good data. Real-world data is messy. Photos are blurry, text has typos, sensors malfunction, humans make mistakes when labeling examples. Data scientists spend 80% of their time just cleaning and preparing data, not building models. Consider autonomous vehicles. They need to recognize stop signs in perfect weather, during snowstorms, when partially obscured by tree branches, when covered in graffiti, and when viewed from every possible angle. That requires millions of carefully labeled examples. The challenge gets worse with edge cases, those rare situations your training data never covered. What happens when the algorithm encounters something completely new? Often it fails spectacularly. This is why Tesla cars occasionally mistake the moon for a yellow traffic light. If you're finding this useful, subscribing literally takes 1 second and helps us make more free content like this. Section 5. Neural networks. The brain-inspired breakthrough. 120 seconds. Now we need to talk about the technology that's revolutionizing everything. Neural networks. These are the algorithms behind image recognition, language translation, and conversational AI. Neural networks are loosely inspired by how our brains work, networks of interconnected nodes that process information. But don't get too caught up in the biology. Modern neural networks are mathematical constructs that happen to be incredibly good at finding complex patterns. Here's the breakthrough. Traditional algorithms follow rigid, predetermined steps. Neural networks are more like vast networks of simple mathematical functions that can learn to represent almost any pattern if you give them enough data and computing power. The deep in deep learning refers to networks with many layers, sometimes hundreds. Each layer learns increasingly abstract features. In image recognition, early layers might detect edges and curves, middle layers recognize shapes and textures, and final layers identify specific objects. What makes this revolutionary is that the network learns these features automatically from data. We don't have to manually program what makes a cat look like a cat. The network discovers whiskers, pointy ears, and fur patterns on its own. This is why neural networks excel at tasks that were nearly impossible for traditional programming. Understanding natural language, recognizing speech, generating images, and even writing code. Section 6. The training process, revealed, 80 seconds. Let's walk through what actually happens when we train a machine learning model using image recognition as our example. Step 1. Data preparation. We collect millions of labeled images, photos tagged as cat, dog, car, etc. This data gets split into training sets and test sets. Step 2. The algorithm makes its first predictions. At this stage, it's essentially guessing randomly. Show it a cat photo, and it might confidently declare it's a helicopter. Step 3. Error calculation. The algorithm compares its wrong answers to the correct labels and calculates exactly how wrong it was using mathematical loss functions. Step 4. Parameter adjustment. The algorithm tweaks its internal weights and biases slightly, trying to reduce future errors. This happens through backpropagation, essentially working backwards through the network to assign blame for mistakes. This process repeats millions of times. Gradually, randomly scattered parameters organize into meaningful patterns that can recognize cats, dogs, cars, and thousands of other objects. Conclusion, 40 seconds. Machine learning isn't magic. It's pattern recognition at massive scale. By showing algorithms enormous amounts of data and letting them adjust their parameters through trial and error, we've created systems that can recognize speech, translate languages, diagnose diseases, and have natural conversations. The key insight? Instead of programming explicit rules, we're programming the ability to learn rules from examples. And we're just getting started. If you enjoyed this deep dive into how machines actually learn, you're going to love our next episode where we break down neural networks in even more detail. The technology powering everything from ChatGPT to self-driving cars. Subscribe and hit the bell. We drop a new deep dive every week, and trust me, the next one is going to blow your mind.